All right, let's go ahead and get started. So first, the midterm is available now. So the PDF is available from the schedule page. So you can download that whenever you want after the class. The time limit on it is 4 hours, which should be way more than enough to do that. So the intention of that is it really should only be a 2-hour exam, that I want to make sure you don't have any time limits or time constraints really on that. And it's due by 1 p.m. on Wednesday, so right before class. Any questions on the logistics of the exam as opposed to the actual contents of it?
Are we turning it in on Gradescope?
You are turning it in on Gradescope, yes. So by hook or by crook, you'll have to create a PDF, whether that is taking the PDF I give you and editing it, whether that is going into Microsoft Word or something and creating a document and just creating a PDF, that'd be fine. So, and then do make sure that you associate the questions with the pages, because that'll make it much easier for me to grade. Okay.
Thank you.
All right. And so let's just look at what we're going to be talking about. So the idea is TD, so one step, temporal difference learning, Instep TD, and then planning, which are the 3 major chapters we talked about. For planning, I will go over again in a fair amount of detail the Monte Carlo tree search. And in fact, what I'd like to do is go over the homework that was due today. Okay.
So, Prof. Rhodes?
Yep.
The midterm is not going to be cumulative then?
This is what the midterm is about.
Okay.
Okay. So it is not cumulative. There will be a cumulative final, but this midterm is not cumulative. Hey, Mazda, can you get rid of your last name, please? Thanks.
Yes. Oops.
Okay. So let's go ahead and get started. Just a refresher on TD. Right, on TD, first, right, TD is a bootstrap method. So this is, let's say, a bootstrap method unlike Mazda. Give me an example of a reinforcement learning method we've seen that does not use bootstrapping.
Okay, so bootstrapping would be like looking at other values to update your current value. So maybe Monte Carlo, where just like
Monte Carlo is a good example. So unlike Monte Carlo, where basically you do entire episode, you get a total reward, and you update your value function based on that. So you're not updating your value function based on the estimates of other value functions, okay? So, but temporal difference learning and also dynamic programming both are using this bootstrap method. So we have on policy prediction, right, where we're just looking at what's the value of states. And here we start in a state, we take an action, we get back a reward, and we're now in a new state S prime. And so we just take, this is our R plus gamma V of S prime is our target, right? And this is our current. And this moves us alpha of the way, right, from our current to our target. For Sarsa, we're actually updating Q values here. So, right, we basically starting in an STAT, we get a reward, and then we take, we get a new state and we choose a new action. And so we are taking our target as this reward plus whatever we think the value of this action is, the state action pair. So that tells us really what fits in here into this space is Q of the new state and the new action. Discounted, of course, appropriately. Okay. If we're looking at Q learning, the difference is right? This part right here, the whole rest of it stays the same, and it's a question of what is our target? That is, what is our estimate of our total reward? And in the case of Q learning, our estimate of a total reward is going to be basically looking at the maximum of all the actions that we could take at our new state, right? So this will be the max over all actions of all the possible actions at that new state. And then for the expected Sarsa, again, we still are taking the RT plus 1. We're still discounting, but now instead of looking and saying what action is our policy choosing at this state, we're instead looking and doing a weighted average, right? So we're doing a weighted average based on our pi's. So this is the pi of, let's say, A prime given S, and these are the various pi values, and then these are Q values. So this then is the sum over all A of the probability of taking a particular action in this state times the Q value of being in that state and then taking that action. Okay. Questions on that?
Yeah, Professor, I have a question.
Shoot.
Could you talk about why Q learning is considered off policy and how expected Sarsa can be both like either on or off?
Sure. The Sarsa is off policy because of the fact that, sorry, Q learning is off policy because of the fact that right here, we're not actually looking at the action. The Q value that we're updating isn't based on the action that's being chosen according to the policy, right? So the policy that we're behaving on takes us to here, right? So that basically says, well, and even the action doesn't really give the policy. So this just gives us a particular transition. So we happen to get an action in a state, and that gives us a new state and a new reward. And then we don't use the policy to decide what action, as we normally would here, right? Instead, we just say, what would the best thing to be in this case? So we are actually estimating Q star as opposed to Q pi. Does that make sense or not?
Yes, that makes sense.
Okay. And for expected Sarsa, the same thing is really holding true. The fact that we're not looking at what does the policy we're behaving on do down here. We're looking on the policy that we're interested in. What would it do? Right? What state action pairs would it go to? And then we can go ahead and use those values.
Gotcha. Thank you.
Mm-hmm. Okay. I remember the maximization bias. The maximization bias basically was the fact that if we have these random variables, right? These are random variables because they're being initialized via sampling, right? So we're doing these sampling to get these values, and so we may have some particular unlikely trajectories we're going through updating the Qs, and so particular Q values may be are a random with respect to the actual Q values. And so if we have several random variables, you know, here, here, and here, and we take the maximum, let's try this. So we take a sample from each of those. And the sample happens to be, I don't know, this sample and this sample and this sample. Then this guy is our maximum bucket, right? It's the queue with the maximum action value. But this red value is not a good estimate of its true value. A better estimate of its true value would be something like this, right? So we go ahead and use the red to choose which of the queues to use. And then once we have done that, we decide, okay, this is the one we want. Now, how are we going to get an unbiased estimate of it? Okay? Because what we ended up with was a biased estimate because of the fact that we're choosing the highest one wins. And so therefore, we're biasing values high. So we want an unbiased estimate. And so we'll go ahead and have a separate estimator Q sub 2. Okay? So we will go ahead and use the argmax of Q sub 1 to tell us which bucket to use, that is, which is the best action. And then we'll use this unbiased estimator Q2 of what its actual value is. Okay? So we just have two different Q values. We are updating their estimates independently. So we're not using any of the same samples to update both Q1 and Q2. And then that allows us to remove this, this maximization bias. This has nothing really to do with temporal difference learning. It just has to do with the fact that if you're taking samples and you want to find the maximum bucket, you can do that. But to then say the value you use to choose the maximum bucket is also a good estimate of that bucket's value is biased. Questions on that?
I have a quick question, Prof. Rhodes.
Shoot.
So with this drawing, or just kind of in general, we know that the max is going to be biased, but do we have like this guarantee that even though we are like always choosing the max, the thing that we ultimately choose will probably still have the best average? Is that just kind of like true in expectation?
In expectation, that would be the case. In any individual case, that in any particular individual choice, that isn't the case.
Right. Okay. So that would be like picking the tallest baseball player and like a point guard.
I know what picking the tallest baseball player is, and I don't know what point guard has to do with that. I don't know much of it.
Oh, I mean like a shorter basketball player. But I think
Yeah.
okay, I think I see what you're saying.
Yeah. Okay.
And then one other thing for the unbiased estimate of Q is, do we always have that estimate being updated, or only when we are choosing?
Yeah, we're always going to be estimating that. So what we're going to do is, just as we're going ahead and updating Q, we'll just 50% of the time we'll update Q1 and 50% of the time update Q2.
Oh, got you. Okay.
Definitely not every other time, because then that may, we may run into issues with, you know, if we're bouncing back from one state to another state, something like that, then we may not be independent. So we'll just, with 50% probability, update one or update the other. And then when we update one, we'll basically use the other for the unbiased estimate. And we're updating Q2, we use Q1 for the unbiased estimate. Okay. So Instep TD, again, remember, we always have this difference between prediction and control, right? Where prediction is basically estimating state values, and control is estimating action values. Now, control is this idea really of deciding what to do, right? As opposed to just knowing how good is it to be in a particular state, deciding what to do. And so when we're deciding what to do, we want Q values. So for deciding what to do, We want the Q values because unless we know the dynamics of the environment, having V values, right, having state values doesn't actually tell us what to do. Even if we knew the value of every state out there, if we're in a given state, we still don't know what action to take because we don't know what states it might lead to. Whereas the Q values will give us the correct value. So back to the TD prediction, it's really useful always to be using these backup diagrams because these really tell us what to do. So if I look here, let's see. I can look at the rewards I'm getting. So I'm getting RT plus 1, RT plus 2, all the way to RT plus N. And that is basically these values here. We discounted appropriately, right? And then the question is, once we get all of those N rewards, what's kind of the remaining reward that we're going to get after that? And the idea is, of course, look at the value of this function. That will tell you what's it worth being in state T plus N. But of course, we got to discount that appropriately since it's N steps down the line. Okay, so G T plus N is the total reward. To T plus N. And we have our standard update. This is our target, and this is our current. And we move alpha of the way from our target to our current, right? So every one of the updates looks pretty much like that, right? And this just provides us a computational way or programmatic way to do the computations we just saw on the previous page.
Prof. Rhodes?
Yep.
Could you go back one more slide?
I'd be happy to.
Could you explain, something that's always kind of tripped me up is when we're running Instep TD, is that we have to simulate an episode, right? And we simulate a full episode?
No, we don't have to simulate an episode.
Okay.
So we've got to simulate. So if we're doing Instep TD, normally we would want at least N steps. We can do it with less than N steps, but normally we want N steps, right?
Okay.
So basically what we'll do is we'll take a step, and let's say we're doing 10-step TD. We take one step. We don't have enough information yet to calculate anything, right?
Right.
Until we take 10 steps, we can't calculate anything. Once we've taken 10 steps, we can go back and calculate that first, update the first Q value.
Okay.
Right, or V value.
Mm-hmm.
And so we would then basically look back in time over the previous 10, look back 10, and then calculate that first one. And then once we've taken the 11th step, we can update the second one, and the 12th update the third, and so on.
Okay, and so you keep going that way until you've completed the episode?
If it's episodic, right, if there's a termination, it would complete. Otherwise, we could just keep going either indefinitely or for as many steps as we wanted, and then we could start another episode.
Gotcha. Okay, thank you very much.
Sure. Other questions on the Instep TD? Not sure why this looks all funny, but it does. So let's look at the Instep Sarsa, right? So the Instep Sarsa, we start at a state and action pair. We get a reward T plus 1, we get a reward T plus 2, all the way to a reward T plus N. And then, so again, the difference here is that we're doing control, so we're using Q values instead of V values. So we started at a state action pair, and we ended up at a state action pair. So it's action T plus N, state T plus N. So we're going to basically use this for determining the value of things n steps beyond. So we'll use n real rewards and then this estimate for what happens after that. Okay. So for Instep Sarsa, we need to basically fill in. We've got our t plus 1 plus a discounted t plus 2, discounted t plus 3, all the way to a discounted t plus 1. And then we're going to have a discounted what's it worth being in that last state action pair. And that'll just be Q of S t plus n a t plus n. Questions on that? Okay, for expected Sarsa, the difference is at the very last step, right? So we still have everything before this is the same, rt plus 1, rt plus 2, all the way to rt plus n. Right? And notice here how, right, I'm not just randomly putting labels on things, right? The open circles are states, the closed circles are actions, possibly labeled with the state before it. The rewards come after we take an action. So we get down to the rt plus n. And then once we're in state t plus n, instead of saying what action would the policy actually take, we say what are the probabilities of pi. So these are all our pi's and these are all our q values. Okay, so it's just like a one-step expected Sarsa. The difference is instead of having one reward before doing the weighted average, we have n rewards before doing the weighted average. So this must be a sum over all A of the probability of taking a particular transition given we're in state S sub t times the reward for being for taking that action from that state. And same old update function. Except this is not right here. So let me erase this. And the reason it's not right is it's not S sub t, right? If I go and look at our diagram, trying to zoom in, right? It's this guy that I'm interested, S sub t plus n. So let me go fix that. I apologize. So it's S sub t plus n, right? The probability of taking particular action in that state times then what's it worth being in that state.
Professor, could you remind me of the significance of the lowercase q versus the capital?
One is smaller than the other. There's no distinction. I just didn't remember which I was using.
Okay, thank you.
Yep. Other questions? Does this would make sense? And right, we could actually do this calculation without the formula, right? Just by looking at the state at the backup diagram, we could just look and say, okay, we're going to calculate again the rewards. We know we need to discount them appropriately, and then our final value. In this case, it's one final value, and it's a t plus n. So we know it's the q value of s t plus n, a t plus n. If we look at the expected Sarsa, we'd have everything the same, which is all the rewards, plus we know when we have a fan out here that the fan out means do a weighted average. So we're doing a summation. Okay, so from the backup diagram, you could easily regenerate the update equation. Questions on this?
Could we have like importance sampling if we wanted to do n-step expected Sarsa, or n-step Sarsa, I suppose, as well?
So we could do importance sampling, yes. So this is assuming that we're on policy. If we want to do off policy, we need to take into account, see, if we look back a second, in the case of expected Sarsa, one-step expected Sarsa, it works on policy or off policy, right? And the reason for that is there's nothing in the one-step case that depends on the policy, right? We have a state action pair, but our whole definition of Q of a state action pair is the action is independent of any of the policy, right? The first action. And then in the expected Sarsa case, we fan out and look at pi, our target policy. Why we have to take into account the importance sampling for n-step expected Sarsa is because of these guys in the middle, right? The fact that we're getting some subsequent actions that are clearly based on the behavior policy, okay? So if these were actions that were very common in the behavior policy, but uncommon in pi, our target policy, then this would tend to overrepresent the rewards that we get for this state action pair, STAT. And similarly, if they were very unlikely in our behavior, but very likely in our target, then we would tend to underrepresent these. So therefore, we do need to go ahead and do importance sampling. So this is importance sampling. And the idea is for every state action pair, look and see what's the probability of it happening in the target policy and what's the probability of it happening in the behavior policy. So if it's likely in the behavior and unlikely in the target, then we'll have a very low ratio, and we will then discount or reduce the reward that we get by that amount, right? So that's this guy here. So this is the overall ratio, very similar to what we were doing, for instance, in the Monte Carlo, right, where we looked at using importance sampling ratios. And then we can also look at the per decision, right? The idea here is if we are in a state in action and then we take another action, so the probability of doing this, right, is B of AT plus 1 given ST plus 1. And then that gives us out a reward. So we have reward RT plus 1, reward RT plus 2. The key is once we've gotten a reward of RT plus 2, any of the subsequent ratios don't matter. Okay, and that's the per decision part of this, where we're actually looking at a specific ratio that is a ratio for a specific choice. And that's going to affect that's going to affect any subsequent rewards, but it can't affect prior rewards. Okay? So the first reward is going to be for V values is going to be affected, but for Q values is not affected, right? Because the very first reward you get is independent of the policy because of our definition of Q, right? So this is the action values, which is Q of STAT, right? Is we take action AT and state ST and then follow policy pi, or sorry, follow policy B. So our first action, our first reward is independent of our row. And then our remaining rewards are, of course, both discounted by gamma and also adjusted by the sampling ratio of pi of AT plus 1 given ST plus 1 over B of AT plus 1 given ST plus 1. And since this is recursive, this is going to affect all the following returns. And then the subsequent ratio is going to affect the returns after that, and so on, right? So the last ratio is going to just affect one reward. Questions on this? All right, so yeah.
So I had a quick question.
ahead, Jay.
From the importance sampling, why does it go to t plus n minus 1 instead of t plus n? I remember it was mentioned before, but I forget why.
Yeah, so what happens is, sorry, you're talking right here. Where are we talking about?
That was a couple slides back.
Let's go. How did I? Yep, so let's look at here. So we're saying t plus n minus 1. So the t plus 1 is because we don't care about that first action, right? This is the Sarsa case. And we don't care about this action. So this, we don't care about this policy. Okay, because of the definition of Q. So that's why we've got the t plus 1 here. All right. The last action, so this is AT plus N, we do care about. That is, we care about the probability of choosing that action under the behavior policy versus the target policy. In the case, however, of the expected Sarsa, we are not following a policy here. We're not following a target policy, sorry, a behavior policy. So we are not, as we do here, ever looking at AT plus N. Because instead, we look and say, let's do a weighted average. So at the very last step, we say, we don't care what the behavior policy would have done. We instead look at all possible actions and just take the weighted average. So that's why it's a -1 here, because we're not taking that last one. So the +1 is shared between both Sarsa and expected Sarsa because we use Q values. The expected Sarsa has a -1 because at the very last step, we don't actually follow the behavior policy. Instead, we just do this weighted average. Does that explain that, Jake?
Yeah, that makes sense. And then this could be ordinary or weighted sampling.
We don't really have a good way of doing the weighted sampling for TD. So this is ordinary. Remember, though, one thing we did do with the weighted sampling was try and reduce the variance, and we have an alternate way to reduce variance. So the alternate way to reduce variance is with these control variates. So the control variates don't change the expected value, but they reduce variance. Okay. And so for the state values, right, we used to have it's rho of t times the reward plus the discounted next reward. And here, what we want, so if the row T is ever 0, right, then what that causes is the target now goes to 0 for there and beyond in the total reward, right? So as we're going, if at any point we have a row equals 0, then that basically kills off everything beyond this, okay? And so what happens there then is that we are all of a sudden changing the target to be 0, which means we could have high variance, right? If we have a non-zero current value and we now say, oh, we want the target to be 0, or at least a portion of the target to be 0, because a big portion of it, right, is set to 0, then that will tend to move that estimate down towards 0, which is increasing its variance. So instead, what we say is, if it would be 0, leave it alone. Okay? So if at any point we have a row equals 0, let's just take as an estimate for this entire thing, estimate this as the value of this state, right? The state where row is equal 0. So that will tend to say, if the row is 0, right? If this is some behavior that, some behavior that would never happen in the target policy, then just leave that state alone. And that's really what happens here. In the extreme example, if row of T is 0, this whole thing becomes 0. And this now becomes 1 minus 0 and just becomes the value of this state, okay? Which will then tend to leave it alone. The only funky thing about this in the Instep case is this may happen any point along in the Insteps, right? So maybe the first 3 steps, row is non-zero. So we're going to get RT plus 1 plus gamma RT plus 2 plus gamma squared RT plus 3. And then the next is 0. And we'll just say, OK, then plus V times that state. Sorry, not V times that state, the value of that state. Does this make sense? And of course, this is a weighted average here, where if row T is not 0, but it's just extremely small, then we're going to take this extremely small estimate of the remaining part of the n steps of the episode, and we'll mostly use the V. Questions? So we have something similar for the Q values. So where for the Q values, we have so here is our row, and we are adding in basically this valuation of what we think the state is. We're using a V hat here, sorry, a V bar, because we don't really have a V value, right? What we have are Q values. So we have Q values, and we want to estimate V of some state. How do we estimate V of some state? We estimate it, here's our estimate, just by taking the weighted average, the weighted sum of our Qs. So we look for that state of every possible action we could take and sum those together. So this is going to end up doing the same thing of reducing the variance without changing the expected value.
Prof. Rhodes,
Yeah.
for the control variant, should we have like a 1 minus rho when we're multiplying by the gamma
So
for the v of t?
yeah, we would have to look at the, well, the short answer is no. We could go back and look at this lecture and look at the derivation of this. So this is the end of sort of a derivation where we got to this, but it turns out to still have the correct. It isn't as easily pulled out so you can see that it's going to just leave it alone if rho is 0. Or actually, maybe it is. So let's say if rho is 0, then what we're going to see is this is going to all go away, right? And so we're going to just left with that the target is RT plus 1 plus gamma times the expected value of the state. So I guess we still don't have that 1 minus so that we can see that it goes away when rho is 1. But we'd have to look back at the derivation for that. Okay. Tree back up, right? So this is a way of not using importance sampling, but still doing off-policy learning. So again, the pictures are worth 1,000 words, right? So here we've got, this is like the expected Sarsa, except we have the expectation at every level of the tree, or at every level of the n steps. Okay? Since it's at every level of the n steps, we're going to get away with not having to use importance sampling. So what we do is we look at basically every leaf. So these are leaves. And we are going to sum together the weighted sum. So we're going to sum together all our rewards, appropriately discounted, plus our leaves, appropriately weighted. Okay. And I guess what I want to say is we're going to weight appropriately each thing in red. Okay? And the appropriate weighting is going to be what is the probability of having gotten there under our policy. So it's the probability of reaching whatever that thing is under pi. So if this is action A, the probability of getting here is pi of A given st plus 1, right? And its value is just the q value associated with that. If this is action C, the probability of getting here is pi of C given st plus 1. And the probability of getting here is pi of at plus 1 given st plus 1. And the probability of getting here is the probability of having gotten to its parent, which is this guy, times the probability. So let's say this is d. This is pi of d given st plus 2. So we are going to weight let's see. we are going to weight these guys according to just whatever the pi is. And then we're going to also weight the probability of choosing actions. Okay. And then any given leaf, we just multiply all the greens that it took to get there from STAT to the leaf. So let's look at that recursively. We're going to say we are going to take our reward, right, which is this reward, unweighted, and then we're going to, of course, weight by our discount factor, because we're not getting the rest of this to the future. And then we're going to take the leaves at the first level. So it's going to be this leaf and this leaf. And that's this. So it's everything but the spine, right? Not the spine. That is not the actual action we took. So we take into account what would have been the probability of taking the other actions times the reward of having taken those actions, or the value of having taken those actions. And then we also discount, again, the action we did take. So this is the action we did take. And this guy is going to multiply by everything else down in the tree. Okay, so if we're at the very bottom leaves of the tree, we're going to have pi of AT plus 1 ST plus 1 times pi of AT plus 2 ST plus 2, all the way to pi of AT plus n minus 1 ST, ST plus n minus 1. Okay. Does that concept make sense? Questions on that?
I have a quick question.
Yeah, go ahead.
So when you refer to A not equal to big A T plus 1, is that A only at the first level, or is that at every single level of the tree backup?
So the key is this guy is recursive, right? So basically, this is the first level. Whoops. And then as we enter the recursion, then this is going to be the second level. And then as we enter the recursion again, it's going to be the third level and so on. So each of them is going to have a factor of this factor right here added on times each level. So at the very first level of leaves, we don't get this factor. We just have a single gamma. At the second level, here, we inherit this first factor of gamma pi of AT plus 1, ST plus 1. And then we multiply by this and this. So we'll multiply by another gamma pi of A comma ST plus. It's going to end up being a 2 due to the recursion. Does that make sense, Jake?
Yep.
Nazna?
Yeah, I just have a quick question about like notation, mainly between like H, big T, and yeah, those two in particular. Like, what exactly do we mean when we say the horizon?
T is, so let's see. T is usually means the end of the episode, right? So if we're looking at a 10-step TD algorithm, and we have an episode of length 100, and we're talking about looking at step 95 and on, then we're going to have to be using the minimum of either sort of the 95 plus 10 or t, which is 100, which is the length of the episode.
Gotcha. So h is just t plus n. Little t plus n. I mean.
Yeah, I'm having to remind I don't think we're using h anywhere in our terminology here, but I believe that's right, that h is t plus n.
Cool. Thanks.
Okay. If I were doing this, I would be tempted, so if I had to actually calculate this, I'd be tempted to I'd be very tempted to use the diagram and calculate this based on the diagram than I would to be using the formula, okay? Especially the recursive formula. Because I think from the diagram, it's really clear to see how for every single leaf, you're going to come up with the appropriate both gammas to use and pi values to use. Okay. Instep, so the Q of sigma is just this blend where at each particular step, you can choose to either do the sort of expectation, or you can choose to go ahead and do importance sampling. So here you would do importance sampling. Here you would do the weighted sum. And so you can go back and forth between that. I would say you need to know the idea of this, but you don't need to actually be able to carry out the calculations. All right, and then finally we got into planning. So in planning, we have distributional models and sample models, right? So distributional models tell you they give you basically the probability distribution. That is P. So you know what the probability is of S prime and R given SA, okay, for all possible states and actions and rewards. A sample model is simpler. Right? A sample model just says, given an S and A, I can obtain a S prime comma R with correct probability. Okay. So a distributional model is clearly more powerful than a sample model, because if you have the probability distribution, it's very easy to choose samples. But given samples, it's not necessarily so easy to come back with a distribution. And planning basically takes a model and through planning improves a policy. All right. So direct RL, right, takes experience and improves a policy. So the idea of planning is we don't have to be using real experience, or at least we may have had some real experience in the past. So there may have been some experience that influenced this model. But once you have the model, you can use it on its own to be improving the policy. Okay. And one example, right, is just keep a big table of states and actions, and have in here, so this is our model. And basically we get back S prime comma R pairs, right? So every state and every action, we keep track of what the last state and reward that we got from doing that. So it's a very simple model. It's tabular. So that means it only works with small state times action space, right? And in this case, it assumes that it's deterministic because it's only keeping one next state and reward for a given state action pair. And so the idea is it looks very similar to direct reinforcement learning. However, there's no use here of the environment. We don't say yet how we built this model. So we still need to figure out how to build this model. But if we have the model, then we can pick a state in action, we can go into the model, we can get what our next state and reward we think should be, and then we'll go ahead and do Q learning based on that state in action. Okay? So the DynaQ shows us what we're going to actually do. So we still have the same model. So this model is still S, A, and in here is S prime, comma R. And what we do is we take an action. So when we take an action, this means in the real environment, okay? And we here do direct reinforcement learning. We update the model. And then we do n steps of planning. And there's no reference to the environment here. We're just taking the model and improving the policy. Okay? Yes, this looks really similar to this. We're updating Q in exactly the same way. The difference is, in one case, we're taking real actions in the real environment and getting back real rewards and real new states and updating based on that. In the second case, in the planning case, we are taking fake actions in our fake model and trying to say, what do we anticipate would happen if we took this action in this state? What reward do we anticipate? What new state do we anticipate we'd be in? And updating our same Q value based on that. Questions on that? DynaQ Plus. The problem with DynaQ is it can get in a rut, right? It can basically get a model that's out of date if you have a stochastic environment. So if the environment changes, I don't mean stochastic environment, I mean a non-stationary environment. So if the environment changes over time, the model, we may just be happy and think one thing when actually the environment has changed. And so the model is out of date. And so it adds an exploration factor that encourages exploration of transitions that have not been observed in the real world for a while. So this is how long since we tried SA in the real world. And the longer it is, the larger the bonus we're going to give. Okay? And that will encourage eventually the real world interaction to try that. And that will either confirm, yes, it's the same old reward and state we're accustomed to, and the model won't update. And then this exploration bonus will go back down, and we're less likely to do it. Or we'll get a new value from it, and that may then update things.
So this update is only applied in the planning stage, not in the when you're actually interacting.
Always. And here's why. Let's say it only happened in the, let me back up a second. I take it back. So this is, let me think about this a second. So if we do it in the planning stage, so if we do it just in the planning stage, what that will do is bump up Q of SA, right? And it'll bump up Q of SA enough that it'll be chosen in the real world action choosing. Yeah, the reason it only happens in the planning stage is because what's the value of tau if we just chose SA? It's 0, right? Right, so, or I'll put it a different way. It'll be 0 right after this. So the question is, where do we, since Q of SA is going to go up from planning, we don't really have to have it happen in the environment as well. It could happen in the environment or not happen in the environment. I'm not sure it's really going to matter whether we do it in either case, but it's very important to do it in planning. Having one extra bump of Q, I don't think is going to hurt if we actually do it in the real environment as well. Does that explain that, Jake? Yeah, it shouldn't matter in the big picture. All right, sampling. So how to decide, so in planning.
I'm sorry, I have one quick question too.
Go ahead.
So in one of the homeworks, we were looking at like total cumulative reward for DynaQ versus DynaQ with like the planning bonus. And I didn't quite understand why the total cumulative reward was always better. Like, does the bonus have any impact on, I guess the bonus doesn't change the rewards that we get at all. It just elevates all of our state values.
Well, the bonus is going to change how we actually act in the environment, right?
Okay.
And so it's going to basically be this, we will tend to be more exploratory than we would otherwise be. So the reason it would be useful, let's say, in the maze, right, where we're going from, where this is all blocked off, and we have our start state and we have our goal state here. The reason why DynaQ Plus could be useful even here is you can imagine, let's say DynaQ comes up with the following, what it thinks is the best path. It's going to go here and then up and then over and then up and then over and then down and then up. Okay? So that's what it decides is its path, DynaQ. And it's not very exploratory, right? It only is doing epsilon exploration. Mm-hmm. So it's going to tend to sort of wear a groove and use this over and over again. Whereas if we look at the DynaQ Plus, it is going to say, I'm not happy with just trying this blue. I'm going to try all sorts of other paths, right? So it's trying all sorts of exploration, and in that other exploration, it's going to find a shorter path.
Okay, I think I see. So when we're doing planning, if we don't have these sort of planning bonuses or exploring bonuses, we're even like further limited in our exploration just because our model is only based off what we've seen and we're experiencing less often.
Partly, I guess the other thing I would say is just this gives an alternate way for the interaction with the environment to do exploration.
Gotcha.
So.
And then I
Right.
have one more.
It's a
quick
different, just a second, Jake. It's a different way of looking at exploration. So this exploration is not this random epsilon greedy thing. It's instead, let's try things we haven't tried for a long time. So it's just a different kind of exploration. And so the more exploratory, the more likely we are going to be to find a better path. Jake, go ahead.
So I was going to ask, in a non-stationary environment, like, wouldn't DynaQ Plus be worse off because it would keep exploring even though like the optimal solutions already found?
Sure. Yeah. If you had a deterministic environment, you would expect exploration to come at a cost. I mean, it always does, right? So yeah, if you had a completely deterministic environment or stationary environment, you wouldn't want to explore. So exploration bonus would be bad.
Wait, I'm sorry, just to go back on that for a little bit.
Yeah.
So that was part of my confusion is because we had like the 2 stages of DynaQ Plus versus
Yep.
DynaQ. And even in that first stage, we had higher cumulative reward. So are you suggesting that maybe like in the long run, DynaQ Plus will be worse? Like after we found the optimal solution, but maybe at the beginning, it will get to a better solution faster?
Exactly. It's going to get to, yeah. So we could definitely see how it could get to a better solution faster. But there has to be, once it is found the optimal path and DynaQ has found the optimal path, DynaQ Plus has to have a cost because it's going to do more exploration.
Got you. Thank you.
Okay. In the sampling, so getting back to that, so how do we choose which state action pairs to try, basically, right? So we're interested in what happens in a state action. And so this is basically for our model. So this is our model. What comes out of the state action is this new S prime comma R. And which ones do we choose? One, is it uniform, right? This is what we did with DynaQ Plus. And just say, just try them all, right? One is the prioritized sweeping. So the prioritized sweeping basically says, prioritize state action pairs that lead to states with a high change, right? So what that effectively does is once we have made a change that is above some certain threshold, then that will cause the states that lead into those states to then be updated with a higher priority than just some other random states. Okay. And that has the tendency then to, if you had a goal state, let's say that got updated, then we tend to update the states going leading into that and leading into that and leading that and so on. And then the final one of the trajectory just says basically use the state actions use simulated trajectories. So start in a start state and then follow from there using the model. So in these previous two, the prioritized sweeping and the uniform, we take a single state action pair and look at its new state and reward, update Q values, and then go pick a different state action and a different state action that are unrelated to one another. Okay, so we're just moving all over the place. In one case uniformly, in another case prioritized, but still moving all over the place. In the trajectory case, we say, no, let's start someplace and then let's just move. And then wherever that ends up, let's move. And wherever that ends up, move. And wherever that ends up, move. and so on. So it's as if we are taking an episode in real life, but the trajectory is sort of like an episode in model life. Okay. Monocolor tree search. So the monocolor tree search is improving a decision that would be made by the rollout policy. So a rollout policy is some sort of policy that we have. And a monocolor tree search gives us a way of improving the decisions that's to be made. The monocolor tree search is a planning technique that's used on the fly. So you're in a state, you're about to take an action, and you want to know what action to take. You have a policy that would tell you, but you'd like to get something better, right? A better choice of the action than the policy is going to give you. So what you're going to do is look ahead, right? This is the idea of I'm about to play chess. It's my turn to go. I look. As I just look at the board, I think, well, it looks like it'd be good to move my pawn, okay? But what I can do is actually think ahead and say, well, so this is my Monte Carlo tree search. I can say, okay, I'm in this board configuration. I could move my pawn. And then I could look and see, well, what does the board look like then, right? And I could try and somehow evaluate that. And if I move my pawn, then my opponent might move his king, and then I might move my something else. Or instead of moving my pawn, I might move my rook, and I could continue on and kind of see. Okay, so I'm going to be looking ahead, right? This is look ahead. And I would consider it principled look ahead, let's say. Okay. The problem is, as I look ahead, how do I determine how good that state is? And the idea is use this rollout policy. So when you get to a particular state, then just go ahead and say, okay, let's just take random actions until we get to a terminal state. And if you were in a better position than your opponent, then as you average over a lot of these rollouts, you will win more often. Okay. The rollout policy need not be random. You could have a smarter policy, but whatever the policy is, you still, other than the monocolor tree search, should do even better than that policy, or at least no worse than that policy. Okay, because you are actually doing some look ahead. So taking some actual steps in your traversal so that you're closer towards the end of your episode. So the 3 parts, selection, expansion, simulation. The best way to look at this is with our home. Well, let's just talk about this and then I'll go over the homework. So the idea is, first thing we do is we've got a partially expanded tree so far, and we're going to choose a leaf node. So a leaf node is a node with unexpanded children. Okay. And how do you decide that? Well, you are going to look at the average Q value. So Q over N is basically total reward over all of your simulations over the number of simulations. So this is the average reward per simulation. Right? So this is approximately what it's worth to be in that state. The problem is there's a lot of variance here. Right? And so just like in the bandit problem, we want to encourage exploration. So this is exploitation. And the second term is the exploration term. So we look at our parents' number of times they have been simulated versus how many times we've been simulated. If we've been simulated, the less we've been simulated, the larger this bonus is, right? So as N of V increases, this bonus, exploration bonus decreases, which kind of makes sense, right? If we have checked this node a lot and done a lot of simulations, then it's more likely to be accurate compared with its siblings, right? So we're comparing basically N of V with this guy, N of V with this guy, N of V with this guy over N of the parent. And similarly, as our parent number of simulations increases, then our bonus increases, but slowly with respect to the log. So this tells us just this exploration versus exploitation, and we're going to try a child. Once we get to the child, we do the same thing. If the child has unexpanded children, we're done. If it doesn't have unexpanded children, we go down and look at its children. How do we determine which of its children to do? Based again on this UCT algorithm. So we keep going until we find a node that has been unexpanded. Sorry, that has unexpanded children. And then we expand it. So we've got, let's say, this node here. It might have some parents. We get here, it's unexpanded. We'll expand it. So this guy is a selected node, and this guy is the expanded node. So this is just one part of our look-ahead process. And then the next thing we do is simulate. Simulate just means follow the rollout policy until we get to a terminal state. Okay, this gives us a final reward. And then we feed this final reward back. We ignore all the rollout nodes we might have gone through, and we start here. This N is now going to be equal 1. This Q is going to be our reward. We go to the parent. This guy is going to be N plus plus. Q plus equals the reward. And we keep going up. The only confusion is this guy has to be either plus the reward or minus the reward, depending if this is a two-player game on whose turn it was. Okay, because if our final reward was, let's say, a +1, which says that the first player won, then any nodes where the first player played, we want to increment the Q because it was good for them. And any nodes on which it was the second player that played, we want to decrement because it was bad for them. So let me quickly show you the homework because I think that would be useful. All right, so here's the homework. There was a mistake here, I'm sorry, that I hope didn't affect anyone. That should have been an X, and this should have been an O. So first, we need to do selection. Find an unexpanded node. We start here at the root. So just to be clear, it's X's turn to play, right? The deal is X has played twice, O has played twice, and now X is deciding what to do. And he's using the monocolor tree search to help figure out. And we've already done some of this monocolor tree search, right? 7 of these iterations. So we have to look at Q over N plus the bonus. Okay. Well, the bonus is dependent on N and N's parents. So we're looking at these 5 children to see which one's best. okay? Actually, let's even stop. Does the root have any unexpanded children? No. There are 5 places to play. There are 5 children. So if there had been a child we had not yet tried, an action we not yet tried, we would have gone ahead and expanded from the root. But the root doesn't have any unexpanded children. So now we go to the children. Here, Q over n equals 1. Q over n equals 1/2. Q over n equals 0. Q over n equals -1. And Q over n equals 0. These left 3 guys all have the same n value. So their exploration bonus is all going to be the same because their parent n is the same and their n is the same. So therefore, this guy can't be it because we're going to add the same exploration bonus to the Q over n. Similarly, these two have the same n's. And so since this Q over n is 1/2 and this Q over n is 1, this can't be it. And now I would just go ahead and add in and figure out what the exploration bonus is. So on the right, it's 1/2, because I think C is 1/2, times log of my parent, which is 7, over 2. That's this guy's bonus here. And these guys' bonus is 1/2 times root log of 7 over 1. If I throw this into a calculator, I would find that this has the higher UCB. Okay, so that's my selected guy. Now, yeah.
Don't look at the nodes in the 3rd tier when we're making that decision.
Oh, well, so this is my selected guy because it has unexpanded children. So I have to stop. Okay. If this n equals 2 Q over 2 node was all filled up with expanded children, then I would go down to the next level. But it has unexpanded children, so I stop. Does that explain that, Janet?
Yeah, I guess.
Well, so let's look at our expansion now. So this guy is selected. Step number 2 is expand. So how are we going to expand? We're going to create a new child from here. The new child is going to be X, X, O, X, O. I know it's not going to have an O in the right lower corner because we already have a child with that, right? So we already took the action of placing an O in the right lower corner. So we need to take one of the other 3 possible actions. So we'll take, I don't know, this O, okay? But it could have been O in any of the other 2 spots. So this is our expand. And now we do rollout. Okay, so rollout is going to be, O just went, so now it's X's turn, right? Let's flip a coin and, sorry about that. And now it's going to be, let's say, X, X, O, O, X, O. I flipped my random coin and it's an X here. Am I in a terminal state? No. I go again. And now it's O's turn. And I flip my coin. And luckily, O won. 3 in a row. Okay? So that is my particular rollout. X could have won. O could have won. Probably X is going to, if I did this multiple times, X would win more often than O, because X gets to go first, and they can win in 1 move. But in this particular case, O won. So our value is -1. And now we've got to update that into our nodes. We start at the expanded node. We set n equals 1 and q equals, and now we have to be careful. So this state we got to because O moved, right? O won the game. So this is a positive one for Q, for O. Now we go to its parent. N is equal 3, and Q is equal, well, do we want to increment or decrement Q? Well, X moved, X lost, so we're gonna, decrement Q. So it's now down to 1 instead of 2. And then we go to its parent. N equals 8, Q equals, it's going to alternate every other time. So we started at the bottom by incrementing Q, and then we decremented Q, and now we will increment Q again. So this will be -1. This Q value in the root, never used. Okay? We don't care about getting to the root. We're already at the root. We know we're in that state. So this is one of our stages of doing the MCTS. We could do this many, many, many more times. But we're out of time now, we stop. Now we have to decide, okay, now that we've done this MCTS, which action do we actually choose to play from here? We have 5 actions. We could either look at their max Q over N, or just look at the max N. And they actually give different results, right? It's either going to be take this action or take this action. The theory on max N is this is the one we did the most rollouts on. This is the child we spent our most time on. We must have done that because it was most promising. The theory on taking the max Q over N is it's the one that has the best exploitation value. Okay. But it might not have been explored as much as something else. So, questions on that?
So I have a quick question about the whole alternating the signs of the rewards that we backpropagate.
Yep.
So first thing that I want to check to make sure I'm understanding, we only really ever update like three nodes, or is it just the number of nodes that we expanded like ×2?
So we would update the expanded node and the path all the way to the root.
Got you. So that path could be, it could be longer. Like how long could that be?
It could be very long.
It could be very long.
Yeah.
Okay. So that would be when we're stuck in like a process of selection and expansion and selection and expansion.
Yep. Yep. And in some cases of MCTS, you might choose to do multiple simulations for a given expanded node. In the particular one we're looking at now, we do, one select, one expand, one simulate, and then we go ahead and do another expansion and simulate another expansion and simulate. But we could do multiple of those simulates.
Got you. Okay. And then
but every simulate updates from where the simulation starts in a leaf all the way up to the root.
To the start node. Okay, got you. And then with the whole business of like flipping the signs of the queue, is that because like it seems to me like a lot of the states where we update with like the negative reward are never really states for X per se, or never really states where X is about to take an action.
It's true that it's not a state that X is going to take an action. I think the way I might look at it differently is something like this. So, and we don't have an expanded enough tree to see this, but imagine you had a fairly deep tree with connect 4, right? Mm-hmm. Where first player went, second player went, first player went, second player went. As you're going down the tree and you're trying to decide what's a favorable path, like if we're playing, it's not fair to say, okay, player one, I'm going to look at what happened if I played something here. And then I'm going to look at what happened if my opponent did something really stupid, right? You don't want to go down the path where your opponent is really stupid. You want to go down the path where your opponent is playing as well as they can based on what you played. And so that's why you are switching the sign, because otherwise what you would be choosing is the best for you to play, and then the best for you, for your opponent to play.
Okay, that makes
You want to
perfect
be
sense.
the best for your opponent to play.
Got you. Okay, that makes total sense. So essentially, what we're kind of doing is like learning best action state pairs for us and for the opponent.
That's any opponent, exactly. Yeah, yeah. And what you're really looking at then is, given that your opponent is playing as, you're trying to simulate your opponent playing as well as they can, you're saying, what's the best action overall that I can choose, such that I still end up in the best state, given they're playing as well as they possibly can too.
Mm-hmm. So I guess my question was going to be, why can't you just use like the same policy that you're learning for yourself for the opponent? But I think what's becoming clear to me is that given this like tree structure, it helps if you already have that accessible without having to like look up your state, that state.
Well, yeah, that's part of it. The other thing is, really imagine that our rollout policy is random, right? Our policy coming in is play randomly. We're only figuring out something better to do by looking ahead and seeing, well, what if I do play randomly? What happens? And then saying, oh, if I play, really it's, what happens if I take this action and then everything is random? And in this action, and if everything is random, in this action, if everything is random. Well, if I do that, this second action looks best. So let me delve more deeply into that second action. What happens if I take the second action and then my opponent takes another action, and then the rest is random? And so I'm removing the randomness, so to speak, from the beginning of the game, pushing it out and saying, let me actually investigate what happens with specific plays, and then the rest of it random.
Mm-hmm.
And so honing in on what is actually a reasonable action to play and reasonable action for your opponent to play, all having no good policy to begin with.
Cool, thanks.
Yeah. Any last questions?
I had a
Go for it.
okay. So if you keep running this, eventually you'll get to all of the possible state spaces.
You will. In which case, you'll get to choose the perfect action.
And then my other question is, like, in the state, so if you take an action and then you have all the different children that's given to you, is this like a planning thing where you have like a simulated model that gives you the answers, or is it like the actual
It's
environment
not
giving
the
you
actual thing.
answers?
It's, you do have to have a model. So in the case of games with perfect information, you have a model, right? We know the rules of chess, we know the rules of Go, things like that. This Monte Carlo tree search is mostly used for games, 2-player, competitive, perfect information games. So chess, Go, checkers, tic-tac-toe, Connect 4, all that sort of stuff. But you do have to have the model, because you have to look ahead. You have to be able to say, what would happen if I did play this move? But all of this is considered planning, because you're starting in a state and you're saying, what should I play? And then you do a bunch of planning to figure it out. Okay? And this is also just-in-time planning, right? We're not planning ahead of time in other parts of the space. That we're focused very explicitly on, this is the state we're in. We have to make a choice of an action to play in this state. Only plan based on that. Other questions?
Yeah, so one quick question I had was, So after we chose an action, so we chose where to go next, where to put the X, all of this gets completely erased and we start from scratch from a new state, but the other player, from the other player's perspective.
Yes
Is that
and
correct?
no. Traditionally, that's how it was done. But the fact is, if we're choosing to take, we're going to take this action. Let's take this action, okay? So this is the second from the right, okay? If we take this action, we can actually save this tree. We'll throw everything else away because it isn't of use now. But the root of this tree is our new state, right? There's no reason to start from scratch in this state. We might as well keep any computation we did and then just build from there. So I don't know the name for that, but this is saving some state information from the previous Monte Carlo simulation.
Okay, thank you.
And it actually makes sense because if you're going with the largest n, this is the largest subtree anyway. So you're reusing the most information.
Right. Yeah. Thank you.
We are, by the way, going to revisit Monte Carlo tree search when we talk about AlphaGo, and I think the last day of class, because that's a key algorithm in AlphaZero, AlphaGo. Other questions? People, feel free to drop off whenever you want. I know it's way past time, but I'm going to stick around till 3:30.
I had just one more question.
Shoot.
So the Q value of the states, can that kind of be thought of like that's the value of like the action that got you to that state?
So, in this case, it is, yeah, it's really the Q value of the action that got you to that state. Yes. You could just as well call it V, and it's the value of being in this state, because there's not really much of a difference between being in this state or having taken action from the parent to get to this state.
But it's like the value in reference to the agent that took that action.
Yes, in the sense, well, so it is dependent on the rollout policy, certainly. So it is based on evaluating this state in our rollouts according to the rollout policy. So if we had a short answer, yes. Other questions?
Thanks, Prof. Rhodes.
Yeah, I had a question with regards to this. So this is like a special case of MCTS, right? When you have two opponents and you can like kind of act on both of them, right? Because in normal MCTS, I feel like, or like the most general MCTS, you would say that, okay, I'm going to take this action that's going to lead to a state that I don't know. It could lead to multiple states, right? In the case of tic-tac-toe. But here we're saying that if we know it's like a two-player environment, for example, we're saying that, okay, I can actively choose to take a state, like take an action, and then expand on the different kind of things that my opponent could do and act as the opponent. Is that correct?
That is basically correct in that. So you might consider the most general MCTS framework, you would be, let's say not a two-player game, you could just be selecting a node by using your model information to move from state to state to state, right? And then doing rollouts. All of that having nothing to do with your environment. So you do have to know, you do have to be able to get dynamics of, if I take this action, what state am I going to go to, right? You have to have a model
Yeah.
for that.
So for that model, what if that says that, like, obviously it can't happen if you're playing like a 2-player game where you can like, what we're doing here is like the first level is after O plays, the second level is after X plays and stuff like that. Let's say that we didn't have that and we took an action, but that could lead to multiple states, right?
Sure.
So then how is that modeled in MCTS? Or are those situations like, do you not use it in those cases?
Yeah. So the question is how, so if we've got an action, basically we've got a stochastic model.
Yeah.
What happens if we're taking an action and that can lead to multiple states? So I'm just trying to think of how you could do that. So
Like, you'd have to estimate.
Here's one thing you could do.
Yeah.
You could instead you could treat the result of taking an action as sort of a sampling of what state you're in, right? So every time you're navigating through the tree, you're taking the action and it's telling you actually what new state you're in. You're looking at that collection of possible states that action took you in, sort of superimposing that as a single place I could get to by taking an action, right? And then as you're working your way down the tree, different times you go down the tree, you may be going to different places.
Right.
Even though you're taking the same actions.
Yeah.
And then when you do a rollout, it's still fairly reasonable to say, I'm going to assign that to that superposition of multiple states, right? What we'll call the result of having taken action A. We know the results of the rollouts of having done that. So
I see. Okay, so rather than building a distribution model, you're saying like I mean, that would be one way that you estimate what the distribution model is and kind of like treat each case separately. But you're saying an alternative is that you say, let's say I take an action, then I'm going to come up in any number of states, whatever that is. I'm going to label that as, rather than labeling it as the state in which I am, it's more the state in which I reach after taking an action. It's just
I'm going to call that my state of, let's call it in particular, root, and then taking action A.
Yeah.
Right. So I'm labeling it by the actions I took, not by the actual states I got to.
Got it. So then from that like superimposed state, you could go to other superimposed states, and like then you're kind of like building a kind of aggregate anyway.
Yeah, you're sampling this distribution sort of.
Yeah.
That's what you're doing, and producing then a value for having taken those actions.
Got it. Oh, that's pretty clever, actually. I like it.
Yeah.
Okay, but in these cases, I guess most of the times that we're using this Monte Carlo tree search, we're concerned with like these 2-agent models or whatever, fixed agent models in an environment.
That's right.
Got it. Okay.
Yeah, and also normally deterministic environment.
Got it. Yeah. That makes sense.
So yeah, the history of this is coming from these 2-player no hidden information games, where you were trying to construct this tree. You know, you're explicitly thinking it's my turn to move. If I move, what's my best choice, given that my opponent's going to play their best choice, and then they play theirs, given that I play mine. And this is this min-max idea. You know, on your turns, you're maximizing your value, and on the opponent's turns, you're minimizing your value, right? Which is maximizing their value.
Okay, that makes sense. Yeah.
But we're not just directly going through and saying, okay, we're going to expand all of level 1, all of level 2, all of level 3, and so on. We're going to instead make this more principled, looking at promising paths and ignoring unpromising paths, and doing that based on this rollout.
Cool, that makes sense.
Dave, Daniel, you guys have questions?
Yeah, I had a question on the next programming assignment.
Okay.
So if you use the package, the library that you leak, you basically don't have to code any of the tree search itself.
That is exactly true.
And you're fine with that?
Yes. So I do want you to read through it and understand it. And there's not much code to it, really. But yes, I'm fine with that. You are a user of Monte Carlo tree search as opposed to a implementer.
Okay.
Yeah, Prof. Rhodes, sorry, go on.
I was just going to say, if you look at the code, you'll see it's just maps very directly to these 4 steps that we have. Go ahead.
Yeah, so I just wanted to, one thing that's always been a little bit confusing to me is, I even forgot the name of it. One sec. Shoot. Sorry. So for offline policy, for off policy, when we do is it called per decision sampling?
Yep.
Or per decision and importance sampling. So I guess if we could maybe talk about that again, and I remember from the material from the last midterm, how we basically had a target policy, behavior policy, and maybe the reason why this importance sampling is because we have a target policy, but we might not want to always follow it for whatever reason. Maybe it's like expensive or something. So we use the behavior policy, and so we use that, and then make some sort of accurate guesses on how it might relate to the target policy, and that's where this important sampling comes in. But yeah.
So basically, what happens is, so there are a lot of reasons you might want to have a target policy different from a behavior policy. So, I mean, if someone else is driving, for example, they're behaving, you're not behaving, but you can still learn something about driving watching someone else drive, right? Even though they're making some decisions not quite with the probabilities that you would make them, right? But it still is useful to see, you know, what happens if you run a red light, even though you're very unlikely to do it, and maybe your friend is very likely, it's still useful to see the results of what happens with that, right?
Right.
And so maybe, you know, they get a ticket or something else, you would discount that ticket because you're not very likely to have gotten that. But you still want to account for the fact that if you ever did run a red light, you know, you would get a ticket. So yeah, there are various different reasons why you might not be in charge of the behavior policy. Another example would certainly be if you are trying to learn, let's say, a self-driving car from seeing what humans do, right? You're trying to learn a policy that is different from the policy that is actually the behavior policy. So the idea is something like this, right? You want, so you know, if you took the expectation in pi of taking a bunch of samples, right? So let's say, so we're trying to do, let's just do v sub pi of s equals sort of the expectation of taking a bunch of trajectories. Sorry, episodes. Okay. So this is, right, according to pi. That is, assuming you're using pi for making the transitions and choosing actions.
Right.
The problem is, right, we have some expectation with B of our episodes. And that's different from pi. But if we multiply by the importance sampling ratio, then these two are equal. We can get the proper, we can adjust the expectation so that it's correctly adjusted, so we get the correct expectation as if we were using pi rather than using B. Okay, that's kind of a hand-wavy explanation.
Okay.
And so, right, if we take R plus gamma times R, let's just use V right now. Right, so if we're using B to do, so B is our behavior, we end up with V sub B of S and not V sub pi of S, right? But if we multiply by rho, that is the pi of, I should really switch this to Q values. All right, let's make this S sub t plus 1, and this S sub t, and this would be the probability of choosing A sub t plus 1 given S sub t plus 1 over B of A sub t plus 1 given S sub t plus 1. So this does the proper correction. Okay, and conceptually, it sort of makes sense, right? Weight things higher if the target policy is more likely to do them than the behavior policy, and weight them lower if the target policy is less likely to do them than the behavior policy.
Okay. And so in order to get like this value, so like the probability that A sub t plus 1 given S sub t plus 1, and also for the behavior policy, the same thing, we need to have some sort of model, right?
Not a model, right? Because so a model models the environment.
Mm-hmm.
We need policies, and policies really are, we need the policy, let's call it dynamics or probabilities. That's what we need. We need the probabilities, right?
Okay.
And in some cases that could be easy, right? Maybe we know our target probabilities, but we also have to know our behavior probabilities in order for this to work.
Okay.
Which is one advantage of the tree backup algorithm, right? In the tree backup algorithm, we didn't need to know B. All we need to know is our policy probabilities.
Okay. And so why wouldn't you know B? Why is that problematic?
Yeah, let's say, for instance, you're going to follow one driver for 1 hour, okay? You see what they do in response to particular states. You see when they turn, you see when they put on the brakes, you see when they accelerate, and so on. But you don't really know the probabilities of these things. If you were watching them for a long, long time, you might have a good estimate to say, oh, in this state, when it's a yellow light, they're more likely to accelerate. They're 2/3 likely to accelerate and 1/3 likely to, put on the brakes. But if you just watched them and they've only done a yellow light one time and they happen to break, you don't know whether that was very likely or very unlikely.
Right.
You just know shit happened, you know?
Okay. Okay, got it. Makes sense. And so then in this same analogy, the pi policy, that's like the probabilities with which I would do all those things.
Exactly.
Is that correct?
Exactly.
And
or the policy you're trying to build that says, what should I be doing? You know, what my goal is to try and come up with a very good policy that gives me the very best outcomes. So if I have a yellow light, you know, maybe it should be probabilistic, but what's the probability I should, you know, hurry through the light as opposed to stop?
Okay, got it. And so would those probabilities always be known to me, or could there also be a scenario where like I don't exactly know?
Since a policy is just the probabilities of taking actions in various states, and since you're trying to model that policy, you do have to know it. I suppose you could have something like a sampling policy where you don't actually know the probabilities. All you know is when you give it a state, it'll give you an action. And in that case, I guess you could build a policy model, I guess. So you've seen what this policy does in lots of different states, many different times, and so you could come up with an estimate of the probabilities.
Got it. Got it. Okay, awesome. Thank you so much, Prof. Rhodes.
You're welcome.
Have a great day. Bye-bye.
All right, see you later. Good luck on the midterm.